Today we're going to be doing the notes on 2.1, which is all about erosion, but specifically by water. So how do we get the landforms that are broken down and built up by deposition, but specifically by water through rivers and oceans and groundwater? This first screen here is a video that just kind of sums up what weathering and erosion is. I highly suggest that you watch it. There's a link to it in your notes. But to sum up the main points, weathering is the breakdown of rocks, while erosion is where all of that stuff, that sediment, those broken down bits get carried away somewhere new. And then deposition is where that stuff gets deposited or put down somewhere new, like in a delta or a sand dune, something like that. So how does flowing water, like in the form of rivers and streams, change Earth's surface? Water is super powerful. So water can definitely cause a lot of erosion. And again, like I just said, erosion is that movement of sediment. So after it gets broken down by getting beaten down by waves or the power of the river current or whatever, that's the weathering part where it gets broken down. But this is where the river actually acts like a liquid conveyor belt and wants to move it somewhere new. Water can also cause deposition. And you can see that I highlighted that part of the word that says deposit. That's because that's your clue to what the word deposition means. Deposition is where all of that sediment and all of that sand, that dirt, that broken bits of rock, where they're put somewhere new. This happens when a river slows down or loses energy for some reason. Either it's bending around a curve or it is entering a larger body of water like a lake or an ocean. We'll see deposition at riverbanks, deltas, and alluvial fans. And that word might be a little bit new to you. You've probably heard of riverbanks and deltas, but alluvial fans might be new. We will talk about what they mean. So erosion and deposition are kind of similar. They're related to each other, but they're actually opposite. They're opposite actions. Erosion is the movement of all of that material and that sediment, and the effect of erosion is that it causes streams and rivers to get wider and deeper, while deposition is where sediment is dropped off, that's put down somewhere new, it's deposited. This is because gravity is stronger than the force of the water. So the strength of the water is losing some energy there. What they both have in common is that they shape some major landforms that we have here on Earth. So this erosion and deposition by rivers is a lot of how we got a lot of our landforms on Earth. So what can determine how much a stream or river can erode? Because not every stream or not every river erodes the same way. So there's a lot of factors that go into how much erosion can happen at a time. First is the gradient of that river. The gradient is just how steep is the slope. So obviously we're going to have steeper gradient in like mountains and things like that. Where you have a steeper gradient, you're going to have a lot faster water movement. If you have faster water movement, we have more energy. And we just talked about this when we talked about kinetic energy. The faster an object is moving, the more energy it has. So the more energy that this water has, the more ability it has to do work on the rock and soil, which will break it down and move it somewhere new. A gentle gradient, so like a flatter river, is going to be a lot slower. It's going to have a lot less energy. It's going to erode the land a lot slower. It's still going to erode. It's still going to make some landforms, but it's going to be a lot slower than those faster, steeper gradients. This is just a graphic to show you what I mean about steep versus gentle gradient. Steep gradient would be like high up in your higher mountain elevations. Gentle gradient would be probably like on flatter land. The next feature that can determine how much a river can erode is the load of the river. When I say load, I'm talking about the particle size. So, like, is that river carrying fine sediment, or is it carrying pebbles and rocks and maybe even boulders? Faster streams have more energy, so they can carry larger particles, so they can carry those rocks and pebbles. Slower streams like creeks, things like that, they are going to be carrying smaller particles like that fine silt and sediment that you might find at the bottom of a muddy creek. So you're going to see a lot less erosion. Discharge is the last factor that we're going to talk about here. Discharge can change from day to day as far as how much water the stream can move at a time. And we know that we can change how much water goes into a stream by the weather. Well, we can't change it, but the weather can change it. So the amount of discharge in a river is just how much water that stream is carrying. If there's been a recent storm, or in the spring, if there's a lot of snow melt at the top of a mountain, you're going to get more water in that stream. The more water you have in the stream, the faster it's going to move. The faster it's going to move, the more energy it's going to have, so the more erosion it's going to have. Okay, so again, reasons for more discharge would be snow melt, storms, things like that. You're going to have less discharge in streams at like a drought time, things like that. So as we get more water, here's a note at the bottom of this slide, as we get more water and more discharge in the river, we're going to have more energy. And with more energy, you are going to have more erosion. And with more erosion and more energy, the river's going to be able to carry a larger load, meaning bigger particles. We get lots of different landforms from our rivers and streams. Streams can form themselves as water kind of like breaks down and erodes some soil and rock. And when we talk about streams, we might talk about their stream channels. A stream channel is just the path that a stream takes. So you might find an old stream channel that is no longer active, but you can definitely tell which direction that stream was going because that stream actually carved out a path for itself to flow. If a stream has enough erosive energy, you might see a carving and cutting through rock and forming a canyon or a valley. Canyons and valleys can form as water cuts through those rock areas, typically in mountain areas. Here's a good picture of a river valley in Russia. You can see it's not a very huge river, but it has done a lot of work over the amount of time that this river has existed, because it has really, really carved through this land. This is another video from Minute Earth about why do rivers curve. This is a really, really great video that's going to give you some awesome animations of why rivers get the shape that they have. So this is also linked in your notes. I definitely recommend that you watch this video as well. More landforms that streams can create are floodplains and meanders. Floodplains usually happen, actually both of these formations usually happen in the flatter area of a stream. So we don't see floodplains and meanders too often in like high mountain areas, but where the river is kind of slowly moving through a flatter area. Floodplains happen on either side of a flat river where the river obviously floods. But when that river floods, all of the sediment and stuff that it's been carrying floods with it. So when we see that river flooding and the area where all the flooded water goes on either side of the river, we're going to see all that sediment get put down, get dropped. This is kind of cool because all of those nutrients and all of that soil that river has been carrying with it gets deposited on either side of the river. This is very, very fertile soil, so really awesome for growing some really cool plants. We see some very cool plant life and animal life in floodplains. Not a great spot to build a house, but cool place to see some awesome wildlife. Meanders also happen when a river is moving pretty slowly and it just kind of slowly curves and moves however it wants. Over time, meanders can get wider. So, like the curves will get bigger and bigger over time. And the reason for that is because on the outside of a meander or a curve, the water is moving faster. And on the inside of the meander or the curve, the water is moving slower. Where the water is moving slower, we're going to see that erosion slow down. And actually, the water energy is sometimes slow enough to even drop off some of that sand and sediment. So we're going to see some deposition there on the inside of the curve. Where the water is moving faster on the outside, you're going to see more erosive energy. And so the outside of that meander is going to keep getting carved out farther and farther. Eventually, a meander might get cut off. And we have a video to kind of show you how this happens. But eventually, a meander might get cut off because of so much deposition happening. When this happens, you get these horseshoe shaped lakes right here called an oxbow lake. So this horseshoe shaped lake happened because there was a meander right here. There was a meander that kept carving out until eventually it connected itself right here and deposited enough sediment on the outside of that meander that this part of the river actually got cut off. Kind of cool. This is a video that will show you some real rivers that have meanders and oxbow lakes, and you'll get to see like how they formed. It's very, very cool. It's also linked in your notes. The last thing that we need to talk about as far as landforms from streams are deltas and alluvial fans. They're very similar formations. Deltas and alluvial fans happen where a river really, really slows down and just drops all of its sediment. So if a river's been flowing through an area and it's been carrying all of its sand and sediment and everything, it's going to carry all the way to the end, or a lot of it. It's going to carry a lot of it to the end. When that river slows down, it's going to need somewhere to drop it off. A delta happens when that river slows down into a larger body of water. Like the Mississippi River flows into the Gulf of Mexico, and we have a really huge Mississippi River delta. Alluvial fans happen at the bottom of a mountain where the river has been flowing through that mountain area. And then when it slows down, once it gets to that flat land at the bottom, it wants to drop off a lot of that sediment from the mountain. What they have in common is, first of all, how they form, but also their shape. Deltas and alluvial fans are both fan-shaped because the river just wants to go any direction it can to drop off that sediment. Pretty cool. This is a video, again, from Minute Earth about why rivers have deltas. It does a very good job of showing the animation of how deltas form. Definitely watch it so that you understand how they form. This is a Google Earth view of another very important delta on Earth. This is the Nile River Delta. So the Nile River actually flows northward and into the sea. And you can see, obviously, we know Egypt is a lot of desert because Egypt is where the Nile River is. Egypt is a lot of desert, but in this Nile River desert, we have a ton of green space. You can see this is a satellite view. So you can see all of this greenery. So this is good, lush, fertile soil with lots of water coming to it in forms of little streamlets as the Nile River is starting to let out into the sea at the north. So this is a really great place for people to live because they have access to water and access to fertile soil where they can actually grow some food, which is pretty sweet. Rivers are not the only type of water that can give us some landforms. Another type of water that can give us landforms is groundwater. And groundwater is exactly what it sounds like. It's water that's in the ground. So you might not realize that underneath our feet, underneath like the floor of your house or the floor of the school, where we have um, rocks and soil and all kinds of stuff, there is actually flowing water underneath our ground. Sometimes that flowing water might actually erode the rocks that are underneath the ground, especially if those rocks are limestone. Limestone is very, very common where we live, and in a lot of the United States, um, but it can dissolve very easily in water. So if we have groundwater that is um, flowing through limestone, it's going to erode it away. If that limestone erodes enough to make a big open space, that's where we get those super cool caves and caverns. Caves and caverns, like I said, can form from groundwater just wearing away. And then we'll get stalagmites and stalactites in those caves that form from deposition. This picture here, this graphic, kind of does a good job of showing stalagmites and stalactites. Basically, how they form is we have this big open cave here that was formed from groundwater erosion, but that cave still has some water in it, and it's still kind of damp in there. So as water drips from the ceiling, it's going to leave behind these tiny little deposits of sediment. So then what you end up with is a stalactite. And I always remember it as stalactites hang tight from the ceiling. So these stalactites actually kind of look like icicles. They form a very similar way to icicles, but they're just left behind sediment from those water droplets dripping off the ceiling. Underneath a stalactite, you'll see where those water droplets land, and that's a stalagmite. So you'll see it's kind of a reverse icicle that's getting built up from the bottom. You might even see, if you've ever gone into like a tourist cave, like we have a couple here in Ohio, like the Olentangy Caverns, things like that. We have you might see like some cave columns where a stalactite and a stalagmite meet. They're pretty cool. But caves can be kind of dangerous if they get too eroded. And what happens is a sinkhole. So sinkholes happen when a cave roof gets too eroded and it's worn way too thin, and then it actually collapses in with whatever is like the weight of whatever is on top of it. This happens very often in Florida because Florida is very damp, has a lot of groundwater, and has a lot of limestone, and has a lot of caves. So you'll see examples of sinkholes happening in areas where that might happen. So kind of interesting. Here's just some pictures of some sinkholes, some very unfortunate events. The last kind of water we're going to talk about is probably the most, not probably, it's definitely the most powerful force of all, and that's our oceans. Our oceans can shape our landforms very, very easily and very, very quickly. So our shorelines are shaped by waves and currents. Waves can build up and break down our shoreline. Building up, again, is that deposition, so depositing all that sand and sediment, and breaking down would be eroding our shoreline. The first part of the shoreline that the waves are going to hit, that's what we call headlands. There's some really awesome examples of good headlands, like in the European areas and up in like the New England area. When a wave first hits the headlands, it's got lots and lots of energy. It's got all the energy of the ocean with it. But then that land kind of stops that wave or kind of slows it down. So it's going to eventually slow down. I apologize if you hear the commotion in my house. My daughter decided this is a good time to play her xylophone upstairs. So anyway, the headlands are the first part of the shoreline that the waves are going to meet. Lots of energy at first, and then they'll eventually slow down. Once that water slows down, you will see it losing a lot of energy, and this is where it's actually able to drop off some of that sand in at beaches. Currents are going to kind of direct that water to build up or break down the shoreline. Currents travel in kind of a cool pattern. It's kind of a zigzag pattern because the water travels sort of parallel to the shoreline, and that's what we call longshore current. This causes sediment to move down the coast in a zigzag pattern. I highly suggest you check out the video that's on the next slide, because they are going to go through like exactly how that pattern looks and how longshore current works. Or maybe it's in a couple of slides from now. But these are just some images that show you like the difference between headlands and beaches. Headlands is where like the land sticks out, and then the water's going to hit that first, slow down, and then make a beach in an inland part. Longshore current, the water is going to hit at an angle. It's going to drop off sand, come back out into the ocean. Drop off sand, come back out into the ocean. Again, definitely take time to watch the video that shows that. This is just a like kind of a time lapse, or not even an animation, but a time lapse video to show you how waves can break down headlands. But this would be an example of headlands and then a beach right here. This is also linked in your notes. This is the video that will show you how longshore drift works. Definitely give this video a watch as well. Okay, so we also have some landforms that are created by erosion. And erosion happens at different rates on different shorelines because of what kind of rock is there and how much energy the waves have. We have a lot of really cool sea cliffs, like I said, up in Europe and in the New England area, and also in the Pacific Northwest. A lot of really cool sea cliffs. But sea cliffs happen when the waves kind of erode and make these really, really steep drop offs. That's exactly what a cliff is. So the waves erode and make a really steep drop off. If that sea cliff gets eroded so much that it actually collapses under, then that's going to create this big flat area down here, and that's called a wave cut platform. So a sea cliff that's eroded, making a level platform, is called a wave cut platform. In some European beaches, I guess they're not really beaches, but in some European countries, you can actually like walk out onto these wave cut platforms, and they're pretty cool. This next slide, this guy is going to show you how a wave cut platform actually forms. Very interesting. All of these videos are very short. Definitely give them a watch. Some more coastal landforms are sea caves, arches, and stacks. These happen kind of in steps. So if you noticed a couple of slides back, actually I can go back to it. We have some of these areas where it shows that the sea cliff is kind of getting worn down. That's a sea cave. So a sea cave gets formed when waves start to erode those large holes in like broken areas of rock at the base of a cliff or in a headland. If that sea cave gets eroded enough, it'll actually make a hole all the way through. And that's what we call a sea arch. And that's exactly what it looks like. It looks like a big arch that's going over the ocean. Eventually, that sea arch might continue to erode, and the top of that arch may get broken down, may get collapsed in, and that's where we're left with a sea stack. A sea stack is just like the lonely column that's left behind of a sea arch. So if the top of the sea arch collapses, that's going to leave behind the column of rock that's just called a sea stack. This is a picture that shows a real C arch and then a C stack here. This C stack is kind of worn down a little bit, but this at one point was a cave that was eroded into an arch that was broken down into a stack. This is an animation that will show you how that happens as well. So those are all examples of how erosion can form coastal landforms, but deposition can also form some coastal landforms as well. The one that we're most familiar with are beaches. Beaches are just sand and rock and dead coral, all kinds of stuff that is left behind from ocean waves as they drop stuff off. That's what forms a beach. It's just an ocean wave that lost energy, that needed somewhere to go with all the sand and stuff that it was carrying. So it's going to drop it off. So beaches are formed by deposition. Sandbars are also something that's formed by deposition. Sandbars are formed parallel to the shore. So like if in this picture, a sandbar could be formed like out here. As the ocean kind of bumps up against this shoreline, it's going to lose some energy. It's going to drag some of that sand back out. And as it's crossing back over another wave, it's going to lose even more energy and it's going to want to drop off that sand. So then we get these sandbars that are kind of formed in these lines that are parallel to shore. If those sandbars get built up enough, then we get barrier islands. Barrier islands over enough time can get built up enough. It's just a sandbar that breaks through the surface. But barrier islands can get built up enough that they can become like really awesome towns and cities and areas where people visit. Like if you've ever been lucky enough to visit like the Outer Banks in North Carolina, and there's some barrier islands up in Massachusetts. These are all cool examples that we have right here in the United States of barrier islands that are tourist attractions, like Emerald Isle, Nag's Head, Outer Banks, like I said. Those are all like tourist attractions where there's actually like houses and cities and things built along a shoreline, which is kind of cool. This is our last video that kind of goes through, I believe it's the last video, that goes through like what a sandbar is. It just shows you kind of some examples, okay? So our next section will be about erosion and deposition, but about all of the other forces on Earth, being wind, ice, and gravity, how those forces can cause landforms and help shape our Earth. But for now, that was the 2.1 notes. Make sure you do your vocab and watch all those videos. They're all very, very short and worth your time.